Day number 3 of our Congress. And this is a very special moment. We get to see the recipients of one of the most prestigious awards that ICAS has to offer, the von Karman Award. For the newcomers to our Congress, von Karman is the founder of ICAS, along with the beginnings of the AAA, the JPL at the United States, the Scientific Advisory Board for the Air Force, and so forth. So this award is given in his honor, and this year the award goes to Icaf, the International Committee on Aeronautical Fatigue and Structural Integrity, to acknowledge exceptional achievement in international cooperation in the field of aeronautics. So we have 4 recipients. It's a multinational representation here. So we have Sweden, Brazil, Netherlands, and Canada represented. And each and every one of the representatives will take the stage and give us a little element of what it is that they have actually accomplished during this period of time. So I'm going to go ahead and briefly introduce the 4 speakers, and then they're going to come up, they're going to give the presentation, and in the end, we're going to hold some time for questions. And of course, there's going to be the actual award. And I will ask the president of ICAS to come out for the picture. So our first presenter will be Mr. David Simpson. He comes from the National Research Council, Institute for Aerospace Research. He rose all the way from a researcher to Director General, and his final positions within the NRC included assignment as Vice President, Life Sciences and Information Technology, Vice President, Technology and Industry. He's the editor of 3 books, author of 40 publications and 30 papers, and author of 50 National Research Council reports. And of all our participants here today, he will be a repeat winner of the von Karman Award. So now he gets 2 of them. The next speaker comes from Sweden, Dr. Anders Blom, Swedish Defense Research Embassy and Univer. Currently is on partial leave from his position as Research Director for Aeronautics to work as Program Director for Univer, the National Strategic Innovation Program for Aeronautics. Anders became the Swedish National Delegate to Icaf in 1985 and Secretary of Icaf from 2005 to 2017. He is active in NATO meetings, and he has been awarded the JF Plantem Award by Icaf in 2001. He received the Thorling Silver Medal for Development of Fatigue and Fracture Mechanics, and so forth. Very well accomplished individuals. The third speaker will be Carlos Chaves. Carlos was born in Sao Paulo, Brazil. He graduated as a naval engineer from the Polytechnic School at the University of Sao Paulo, where he got a master's degree in solid mechanics and metallurgy, and a PhD degree in solid mechanics from the University of Tokyo. He is a member of ABCM, Fatigue Structures and Structural Integrity Committee, member of ASME, and the Brazilian delegate to the International Committee, ICAF. And our final presenter, Marcel, he comes from the Netherlands. He's in the Netherlands Aerospace Center, NLR, where he has been engaged in contract research for various national and international customers. He's the delegate to the International Committee of Aeronautical Fatigue and Structural Integrity, and he has chaired numerous meetings and organizational defects. Lastly, in 2017, Mr. Boss was elected the ICAF General Secretary. So we will start with David. David, if you can please join me.
Thank you very much for receiving our presentation this afternoon. We very much look forward to providing you with some information on ICAF. I would like to start at the beginning. Early aircraft were designed statically, but fatigue failures did happen, but they weren't codified into regulations, nor were they part of the design process. In the beginning, Dr. Frederick Plantema recognized this, and in his published paper, Fatigue of Structures and Structural Components, he proposed the idea of ICAF, the need to share data, the need to collaborate internationally. And this resulted in the first meeting in 1951 at the College of Aeronautics, where essentially ICAF was born. The meeting was small. It had, the concept was experts sharing, and sharing in a way that did not violate the political and other sensitivities of the time. The ICAF goal was and still remains to share information for the betterment of the technology. Now, there we are. Sorry about that. In 1952, the first formal ICAF conference was held. And at this meeting, there were 9 attendees from the Netherlands, UK, Sweden, Switzerland, and Belgium. The initial focus was to make sure that these experts, and these were the prime people in the field at the time, shared their information and experiences and created a wider understanding of the failures that were happening. The other issue was to build professional and personal interactions and trust, so that information that perhaps sensitive could be shared without any fear of wide distribution. The opportunity was also there for peer comment on national programs, and as a result of the national reviews that were prepared by the delegates, it was also used internally within the country to educate the rest of the scientific community of what was happening in the country. This was followed by a series of meetings in 53 through 57 around a conference. Now, in 1959, the first symposium was held. This was where we invited papers, or where papers were invited by selected experts in specific fields related to fatigue. So the symposium now consisted of 2 parts. One was the conference, and the next was the symposium. Now, the networking value of ICAF was recognized, and the ICAF has grown from 3 countries to 17, and this has brought forward some challenges. It's not only the number of people that attend ICAF, it's who attends. And this is unique in ICAF, I think, is we have not just the universities and government researchers and that community, but there's also a strong presence from both the civil and military industry, as well as the regulators, senior regulators, trying to get a consensus of what is happening in the world in fatigue and fracture, and build that into the possible challenges from a regulator point of view. This is a major differentiation from some of the other organizations that were forming at the time. Now, the format of ICAF has been modified as time has progressed. It is consensus now that it's 2 days of conference where national reviews are presented, followed by 3 days of symposium, and also the awarding and memorializing of important individuals such as Dr. Plantema and Jaap Schijve, a strong contributor to ICAF, through a memorial lecture and a student award. The proceedings of both the conference and the symposium are, of course, available online or through paper publication. Now, the ICAF, the strong emphasis on relationship building is a fundamental characteristic of an ICAF meeting. There are a lot of social events, and there's a lot of opportunity for the kind of interactions I've seen at the ICAS meeting today. And again, it's a trust-building exercise. Finally, just in terms of logistics, ICAF is an independent organization. It is managed by the General Secretary and the National Delegates. The meetings are organized by the National Delegate in the host country, and he or she is responsible for the full arrangement, from the identification of the theme for the symposium, selection of papers, funding, financing, and as well as selection. So it is a very, very busy time for the national host. I leave you with the summary. I won't read, but the important points that I was trying to make are listed here, and I'll pass it on to my colleague, Dr. Blom.
Good afternoon, everybody, ladies and gentlemen. My part would be to try to give a technical overview of what we have actually done over the last several decades, what's happened in the world, and what were the main technical contributions, and where do we stand today. Since I only have 25 minutes, I have to go fairly quickly. I put in too many slides. I will not read all of them, but you will have copies, and if anybody's really interested, I have written material to substantiate more in detail what I will speak about. So fatigue is a very old phenomenon. It goes back a couple of hundred years. The first work I know of was made in 1829. First serious work is studied by Werner in the 1850s. And at this time there were tremendous many fatigue failures in the world. In fact, in Britain there was published every week the train crash of the week due to fatigue. And when it comes to aeronautics, fatigue was back to the very first flight by the Wright brothers. There was a delay due to a hollow propeller shaft, which was developing a fatigue crack. And on the right-hand side, you see a number of failures. The first in-flight structural fatigue failure occurred back in 1927. And after that, lots and lots of failures occurred. And in 1944, the first US Air Force fatigue test was done. A very famous failure occurred in the early 50s by this plane, which was the first serious operating jet operating at high pressure, so it could fly at high altitude. Therefore, it had a number of unique features, such as twice the internal pressure compared to any other plane at the time. And this particular one, called Joke Peter, was delivered in '52, and I think it was 1st January, 2 years afterwards, that it failed, and it fell down. It was flying from Singapore to London, had landed in Rome, and then crashed outside the island of Elber at about 150 meters. At that time, the fleet was stopped, and a number of factors were investigated. The industry checked some 60 different possible reasons for this failure, and flights were resumed only 3 weeks after another crash happened, also in the Mediterranean, just north of Sicily, at Stromboli. And both these planes had flown only in the order of 3 in 2,000 flights. Then they tried to recover the pieces from the first failure and started to do fatigue tests. And it was soon realized that fatigue cracks did happen, and they came at the corner on this window, which was used at this time to navigate after the stars at night. So basically it was understood already at this time that cracks initiated to the new very high pressure and stress concentrations. Later on, it has also been explained that we had lots of secondary out-of-plane bending due to curvature of the fuselage, which added to that. So the main effect here was basically to realize the importance of stress concentrations. Early on, a number of important contributions to our field were the development of the closed loop servohydraulic test system. That's the best we have, the full-scale fatigue test. A little bit similar to the wind tunnels in the aerodynamics community. Fracture mechanics was started to be used in the 60s, 70s to model fatigue crack growth. And it's interesting to note that the first paper by Paul Paris was rejected in 3 leading journals. And the reason was that people felt that there is no way that a phenomenon as fatigue crack growth, which includes material separation, therefore plastic deformation, it cannot be modeled by a linear elastic fracture mechanics parameter. However, now it's very well understood that as long as we have what is called small-scale yielding, which we normally do at the lifetimes we operate, the stress field at the crack tip is characterized by the first term in the series expansion. This is called the stress intensity factor, and that has an inverse square root similarity. So the stress goes to infinity at the crack tip, but of course yielding will stop the stress from becoming infinite. And the good thing in this is that it's not dependent on planar geometry, so we can transfer data from test specimens in the lab to the structural calculations we do for real aircraft. Finite element methods were starting to be used in the early 70s, and they are our bread and butter today to analyze stresses. And 1974, the US Air Force introduced the damage tolerance concept following two failures of F-111 in '69 and fatigue problems of the C-5A cargo aircraft. And I will only show the F-111 here. Originally it was designed for the service life of 4,000 hours and equally many flights, but failure occurred after only 105 hours. And this happened at a low bombing mission, occurring at only 3.5 Gs, which is roughly half the design limit, so the stresses weren't that big. And the reason, of course, you can see down on the lower corner here, sorry, I can't get this right. You see, on the right-hand side, you have an initial flaw prevalent in this steel. It's a D6 steel, already at the beginning, roughly 1 inch long. And this particular steel is very sensitive to small cracking. So failure occurred very fast. Eventually, the problem was sorted out, and they have done 4 fatigue lives and resumed safe flying. But each and every aircraft had to be tested at minus 40 Fahrenheit before flying, due to the sensitivity to very small flaws. Very expensive. We had failures in Sweden also at about this time. These are due to logistical problems. A hole was drilled very close to a free edge, and this was not forwarded back to the stress office. Very simple to analyze when you know, but it's a logistical error. Another one happened in the late 70s. It's a Boeing 707, which crashed upon landing in Lusaka Airport in Zambia. And the design service life here is 60,000 hours, and as you can see above, it failed much earlier. And this design is quite interesting. It's only the upper and lower quad which are carrying load. The middle part is a fail-safe design. Normally it doesn't take any load, but once one or the other one breaks, the center part can take load, so it's supposed to be a safe, fail-safe design. However, the cracking occurred in such a way that it was not possible to inspect before failure. So what we learned here is that even if you design for crack growth, you must have inspectability. So in the 80s, which is probably the most important decade in terms of structural integrity growth, there was tremendously good funding available in most countries in the world. We could do lots of basic research in fraction mechanics, fatigue crack growth studies on mechanisms, things like heat treatment, you change dislocation structure to get planar or wavy slip and so forth. We did lots of work, especially in Europe, on producing standardized load sequences. Falstaff simulates the loading on a fighter wing, twist similar for a transport wing, the connection to the fuselage. Helix and Felix are helicopter load spectra. Enstaff is the same as Falstaff with environmental conditions involved to test composites. Carlos is for the car industry. These sequences were produced in order to make it possible to exchange data around different laboratories, because load sequences typically are classified, so you can't easily change data otherwise. I think this is still a very good concept. We worked very much on composites then, focused on very basic things like the influence of humidity and temperature. Lots of work on joints. This is still very relevant. Joints are one of the more difficult things to design, especially when you have combined metal and composite structure. And we, at that time, we had very close links to what is called AGA, that was NATO's research and development group at that time. Still exists in a different format, not as successful, I think. Next fail I want to show happened in Japan. A Boeing 747 crashed because the bulkhead cracked, and you got pressure which teared off the fin and vertical the horizontal tail plane, therefore tearing away all the hydraulic control system. The reason for this was that the plane had previously had a very bad landing, introducing damage in this bulkhead. So it was repaired according to what were correct regulations. However, the repair did not occur in the right way. So the left-hand side shows what it should have been, the right-hand side shows the actual repair. What happened was a mistake in the middle part, hard to see here, such that you only have one rivet line carrying load in reality, whereas it should have been 2 rivet lines. So here you see that these 2 bays now, because of the poor repair, have only one single row rivet, and that has less than 70% load capacity than before. And my final failure is the famous Boeing Cabriolet, crashing in Hawaii back in 1988. It was flying from Hilo to Honolulu, and luckily enough, only one person died. More than 5 meters of the roof were just torn off, and one airline stewardess were sucked out, but the pilots immediately made a safe flight, which happened 40 knots too fast, but very well performed. Had this been a composite fuselage, everybody would have died, of course. You can see down, design service life is 51,000 hours and 75,000 flights. If you look on the top, the failure happened at less hours than design life, but more flights than originally designed for. This plane, of course, was bought second-hand from another company, and the mission profile was totally changed. When you fly in Hawaii, you fly very short distances, so you have a different distribution. You also have environmental conditions which are different, and Aloha Airlines did not fulfill regulatory inspections in the proper way, so there were problems with lap splices, and that caused tremendously many small flaws, which each and individual one cannot be inspected, and suddenly they grow together very fast and led to failure. This was the first time observed in reality what now is called the aging aircraft problem, or widespread fatigue damage, which we now design for. And it's particularly important for aging aircraft when you start to fly more than, say, 2 times the original design life. Then you start to get problems with corrosion effects, which will induce small flaws at every single fastener hole. Too small to be found easily, and eventually they can coalesce very quickly. So, during these decades, design principles have changed from static, which was only safety by margin, and that became very quickly too expensive to develop planes much. Then we went to what is called safe life, which is really safety by retirement, also too expensive because you only operate the plane for the original design life. Today we fly much beyond that. Then we went to fail safe, which is safety by design, which is quite tricky. It's now part of damage tolerance design rules, which are really based on safety by inspection. All civil aircraft today are designed for this. Military aircraft, as far as I know, still only in the United States and Sweden. This I don't need to show. This is a simplified chart of structural integrity management, starting to derive emission analysis. How do you want to use the plane? Then you derive the loads acting for those missions. You do a structural analysis to get the stiffness distributions, and then you go in with local analysis at critical points for stress and fatigue life. You produce a product model, and you do manufacturing and service. Then I have loops. The inner loop is structural testing from details up to complete aircraft. At the same time, we have flight testing, making sure that the initial load assumptions were correct. If they are not, you have to go back and redo the stress analysis, which will influence the test aircraft. And finally, we monitor loads on each and every plane, of course, such that we can optimize the usage, different pilots, mission mix, and so on. So, very quickly, what is involved in emission analysis is clearly previous experience, the expected threat, future tactics. This is for fighter aircraft, of course. Various mission types today, lots of new plane are changing mission types. You have mixed fleets, so you do both reconnaissance, air-to-surface attack, fighter roles, and so on. And loads analysis are derived from finite element calculations, computational fluid mechanics, flight mechanics simulation, and of course lots of wind tunnel data. And we have loads of various load cases. When it comes to civil aircraft, the ground-air-ground cycle is very dominant, and we typically design for 60 to 100,000 flight hours or so. For fighter aircraft, the the maneuver loads typically dominate the fatigue life, and therefore we have much larger stresses, and lives are in the order of 1/10 of civil aircraft, 6 to 10,000 flight hours or so. I guess I don't need to go through. This shows typically load entities you want to measure while you fly, especially in the beginning. When you have flown a few thousand hours, you can normally start to correlate with simple flight mechanics data, center of gravity, acceleration, and so forth, so you don't need to do all these measurements. But there are certain areas which are fairly difficult to model, and you still need to do measurements. Structural analysis, always done by finite elements these days. You start with something like this, not very advanced model, only to get the stiffness distribution correct. Then you go in locally in all the sensitive areas and refine the models as needed. This is an area which has grown tremendously, and today we can actually solve any elastic problem you want, numerically exactly. My own research group has done this work for the US Air Force until 2009. We are still working with them, but I can only publish all the already reported things. At that time, we had access to up to 30, 40,000 CPUs. Today, much more. We are far beyond this. We are in the order of petaflops today with the computational systems available. I would say that in the commercial world, it's very hard today to compute more than about 100 million degrees of freedom, because the computational codes do not scale with the number of computers. If you do three-dimensional p-versio finite elements, you can actually scale this. So we have in fact done what I believe are the largest real computations, up to 7 billion degrees of freedom in statistical modeling. Very complicated, but you can do this extremely well today. Full-scale fatigue and damage tolerance is done for each and every new aircraft. Typically, you do full 2 fatigue lives first, then you introduce flaws at critical location and do up to 2 more lives, and then eventually residual strength tests. This shows work in Sweden for the Gripen aircraft, where you see that about 800 initial flaws were installed in critical locations, and a full-scale test can look like this, typically with 120, 140 load actuators. Goes on for many, many years, and you always want this test to be far ahead the flight leader out in service, such that we will discover any possible new mechanisms occurring due to design changes or new materials. In the 90s, we still had decent funding, much less than the 80s, but okay. Damage tolerance and structure became required, as I mentioned, for civil aircraft. Aging aircraft issue became the largest research topic ever in the world. Composites were gradually introduced even more. Now the focus was on low energy impact damage and barely visible impact damage. Structural concepts today look typically like this. You have detachable half wings mounted on the wing carry-through box. Constant wing aspect ratio optimized for speed of the design role. Separated tail planes in US or full delta configuration and controlled by full active camouflage in Europe. Single fin in Europe, twin fins in US, single or twin low bypass turbofan engines, and weapons are mounted on wings and fuselage externally mostly, except for 5th generation planes where you have internal weapon base for low signature. Here, this is somewhat old, I only compared Europe and US. Today, probably the best fighter in the world is being produced in Russia, the PAC-FA, that's also a 5th generation fighter, and China has started to produce several of these. Although in my mind they're still a little bit behind, but that will be changed in the next few decades. When it comes to material, there is a big discussion of composites versus metals. There is lots of gospel at universities that you say, wait, but composites is not true, not until now at least. What you possibly benefit from composites is less inspection, and composites are really only important at intermediate thicknesses. You can't use them for very thin sheets, and for thick sections, you still prefer metals. Metals are much better under impact conditions, and that includes battle damage. So for real war situations, I still would go for a metal wing. But in a certain sense, you can use anisotropic nature to optimize things like lateral deviation, and you could put in sensors for control of damage growth, for example. This I will skip. This is a chart of how material selection has changed over the years. Today you can see that most planes use composites up to 30-35% of the primary structure, but in the next few years, already Boeing 787 is flying with a pressurized fuselage, and the 350 is expected even more composites. If you go back, you see that this was led initially by fighter aircraft, but now even more so for civil aircraft. Also interesting is that in the 80s and before, we had lots of titanium in fighters. We don't do it anymore for various reasons, but now they're coming back as fastener elements. You can't use steel because of corrosion, and you also have it as soon as you have high temperature problems. New material problems, nano-engineered materials are introduced. Again, gospel, everybody believes strength and stiffness is important. Yes, you can't scale that easily to structural applications. So what we want is to look at surface properties, electric, electromagnetic, and so forth, whilst maintaining strength and stiffness. The other thing happening now is that due to health and environmental problems, lots of materials used in the past can no longer be used, so we have to look for new materials, and this is extremely expensive. This I will skip. My final few slides, I want to show what has happened. Every generation of military aircraft, from generation 1 to up to 5 now, has become more and more complex, of course. You introduce more and more systems and so forth. Therefore, the planes are much more expensive. Therefore, you buy less planes. This is just what we did in Sweden. We changed from Draken, 600 aircraft, 1,500 flight hours to Viggen, 300 aircraft, 2,800 flight hours, Gripen, in the order of 100 aircraft originally. In this version, now we're building a new one, 8,000 hours. If you multiply this, it's basically constant. The reason is that we need very long lives to train pilot in peacetime. And when you have very few aircraft, you need longer life. Therefore, I would dare to say that the next generation aircraft, structural integrity is more important than ever, because you want to update these planes. You want to be able to put in new sensors, new avionic systems, new communication suites, and so forth. And unless the structural integrity of the plane will be there, you can't do this. So I have a feeling that at high management and lots of companies now, they feel that they know structures, aerodynamics, flight mechanics, and other things are more important. Maybe not, because there is a load of senior people disappearing from our industry in the next few years. And if you look here, what I find is less funding for military purposes, much fewer aircraft projects. There is a risk for losing experience and repeating mistakes from the past. There is an absolute need for knowledge transfer to younger generations, which is very good with conferences like this. I also see a big risk for trust in huge calculations, despite what I showed, without substantiated input data, load cases, boundary conditions, and structural testing available. Aeronautics has started to become more and more cost-driven, a little bit similar to the automotive industry, but safety should always come first. I think when you fly back, yes, you're concerned about the price, but more important is that you actually bring home your family. So that is important. We are starting to look not only on fixed-wing planes, but more and more on helicopters and systems. There are different challenges here. Helicopters are big fatigue machines, of course, and systems have much smaller dimensions, which causes certain problems. As what it mentioned, we broaden our scope to not only fatigue, but structural integrity, and the reason is, of course, that we already worked on static strength, battle damage, bird impact, corrosion, and so forth. And we wanted to make sure that the most important aeronautical countries in the world, not yet members of Icaf, became so, and those countries are China, Russia, and Brazil, and will be covered by my colleague in the next talk.
Good afternoon, everybody. I will, in this part of the presentation, I will talk about, why the new countries want to join, why they joined actually the ICAF, and the current challenges of civil aeronautics. I have input from Professor Degan Cui, who is the national delegate from China, and from Dr. Boris Nesterenko, who is the national delegate from Russia. The presentations from China and from Russia, they were kept as received, so I will skip this slide. The first question that was given to China was why China was interested to join the ICAF. As Professor Cui presented, there is a huge market demand for commercial aircraft in China. And as you can see from this plot here, there is an expectation of nearly 9,000 new aircraft by 2036. And besides that, China was interested to join the ICAF to encourage the contacts in an international context and to improve their research levels in the aviation fields. China joined the ICAF in 2015 in Helsinki, and after that, China organized a Chinese aeronautical establishment in 2016 that is responsible to organize the academic cooperation with ICAF. As you can see from these pictures, this is a picture taken from this Professor Cui is in the right side, under Blom, that was taken in Finland, and that time Ashak Sylvander was the Finnish national delegate. Here in the right, you'll see, I believe it's the CAE office and all the staff that's working with ICAS now. And the pictures taken below are from the Chinese participation in Nagoya last year. In this slide you can see some recent achievements from China in the fields of fatigue and structural integrity. You can see some coupon tests, some component tests, some full-scale fatigue tests, some overview of structural health monitoring activities, and there is an interesting slide on the left with a panel that is friction stirred, fully friction stir welded. These are some challenges for the China aviation development. Some of them are related to certification requirements for new products, and this will be the same for Russia, I can anticipate for you, and the same for Brazil. And also the application of fatigue and structural integrity theories, technology, materials, and processes into the new products design. And here you can see some new products that are being under development in China. Yes. Finally, this is an overview of some activities related to fatigue and structural integrity that are being carried out in China now. You can see some new materials and new processes like additive manufacturing in the top right. And inspection and structural health monitoring and testings for some specific application. Regarding the Russian Federation, the participation of Russian research organizations, academia and universities, jointly with industrial aviation companies in Icaf, is aimed to close the cooperation of scientists, engineers, and aviation specialists in the field of aeronautical fatigue and structural integrity, share of knowledge and experience, and adoption of the best practice and effective solutions. Here you can see some recent products of Russia, the MC-21 from Irkut, and there is an interesting picture of the lower skin apparently made of carbon epoxy. And the SSJ, Sukhoi Superjet, and the full-scale fatigue test of a wing, I suppose that is from the SSJ. And the third product here is not a civil, it's not for commercial aviation, it's an Ilyushin cargo tanker. As most of you know, Russia has a very strong background in aeronautics. They have their own requirements, they have developed their own requirements. They have a strong background in fatigue theories with statistics background, and they have a unique technologies in full-scale fatigue testing. And also, as Dr. Nesterenko emphasized, they have original approach for aging fleet airworthiness provisions. Some challenges of, that Russia is facing now with their new products are regarding composites and probably hybrid structures as well. The introduction of new materials, not only composites but also metal alloys, and fatigue-related issues on new fabrication and assembly methods. Dr. Nesterenko mentioned assembly and production, and this is something that after I read his presentation, I agree with him. It's not only material, but it's also the process you have to think about. And this, he added this pyramid at the bottom of this, I like it very much, this building block approach. And it shows some recent trends in, for future product development, that this pyramid is becoming something different. It's becoming, or it will become something different in the future. That is this red line that stands for less tests for high complexity, full scale structures and more tests for lower complexity material tests, and with a lot of background from statistical behavior of the material. Okay, this final slide from Russia shows some key activities in the Russian aviation industry related to Icaf topics. You can see some full-scale fuselage tests from SSJ and from MC-21. In this case, in the middle right, you see a set of panel tests. I was quite surprised to see that more than 30 fuselage panels were tested to validate this fuselage configuration. About Brazil, our participation is being supported by ABCM. I wrote in 2015, but actually we were with talks with the ABCM, just to remind you, is the Brazilian Mechanical Engineering Society that is supporting this event as well. We were in talks with ABCM since 2014. And then we presented 2 national reviews in Helsinki and then in Nagoya. And following the ICAF directive, we became an ICAF member country in 2017, last year. We joined the Icaf because, as you could see from this week, there is an expressive aerospace industry, and we work with commercial aviation, executives, business aviation, defense, and consequently it has been leading to an increasing amount of research related to aeronautics and aeronautic fatigue. And the participation of ICAF, I think I can say that from Brazil, Russia, and China, it's very important to keep our communities always aware about what are the recent trends in the fields of aeronautical fatigue and structural integrity. This is our Brazilian delegation. I added on the left, Fernando Fernandez, who works in the RD department of Embraer, and the middle, Dr. Jorge Aleixo. She works mainly with material testing, and as you can see in the right, it's me. And this was a very good, the ICAF was a very good way to organize a network of universities and research institutes and industry inside our country. I am mentioning the organizations that collaborated with a significant collaboration with giving a lot of interesting research data and results for us in the last two ICAPs. Some, like the University of São Paulo, two campuses in São Carlos and in Lorena. University of Itajubá in Minas Gerais, they work with composites and structural health monitoring. In São José dos Campos, there is a military facility, CTA, ITA, that is also a very important research organization, and the Embraer and the University of Ponta Grossa. There are other universities, even here from Belo Horizonte, we already have results, and the network is increasing, and this is very good, very positive. Finally, about the challenges for civil aviation development. First, there is the continued airworthiness for an increasing work fleet. It's not just to develop a product, you need to worry about how to maintain it working, flying safely. That's a major concern, of course. Airworthiness regulations, they are always evolving. I think certification requirements are changing from prescriptive requirements to performance-based requirements, and that's important also to be aware about that. And about materials and emerging materials and technologies. Materials are always changing, as Anders showed, and even aluminum alloys are important, carbon fiber, and so on. As Humberto Pereira mentioned on Monday in his presentation, from the standpoint of requirements and from the standpoint of materials and technology, the bar height is going up. Thank you.
Okay, I'm the last one. Yes, I was speaking a little about the future of ICAF and the challenges in military aviation, and most of the challenges have already been alluded to by my colleagues, so I'll keep it short. Military aviation, and probably most of these challenges also apply to civil aviation. There are a few challenges. First of all, we have very new structural concepts like hybrid structures, combining composites with metals. which entails new types of loading, thermal loading, but also corrosion issues. And corrosion as such is not a particular topic for ICAF, but the effects of corrosion on the structural integrity of structures certainly is. Additive manufacturing, there have been a few presentations on additive manufacturing during ICAS. It's a hot topic, and there are good reasons for it to be a hot topic. But of course, there will be a number of structural integrity issues there. First of all, additive manufacturing entails at least 100 process parameters or so, which really puts some stress on the quality control of this process. But even if you control it right and your product is excellent, additive manufacturing also drives the optimization of structures. In theory, it's possible to optimize your structure such that you have a completely even stress level, so that your component is stressed at the same stress level all over, which is nice from a weight point of view. From a structural integrity point of view, it's a nightmare, because you don't have a few hotspots where fatigue may occur. No, the whole component may fatigue at the same time. And having said that, optimize against what? Military aircraft, civil aircraft as well, military aircraft in particular. The usage of military aircraft usually is very different from the design usage. So even if you optimize the structure for a particular usage and loads, in reality, the usage may be very different. Unmanned aircraft. Unmanned aircraft, they have no pilot on board, they're unmanned. So there's no one to report back whether there has been an incident in flight. Nowadays, military aircraft are usually flown in segregated airspace, but push of having them flying in non-segregated airspace, civil airspace, will be there. You would like to have some form of reporting, some structural health monitoring system on board that could report back to the control tower, okay, it's safe that I can enter airspace. So this will drive the development of structural health monitoring systems as well. And structural health monitoring, well, people have been talking about this and have been developing systems like that for years now. But there's not much flying yet. But this may change with the emergence of UAVs that's taking place at the moment. SHM, at the same time, enables new maintenance concepts like condition-based maintenance, prognostic health management. Traditionally, aircraft are maintained according to calendars, hours, flight cycles, etc. Most operators would like a condition-based maintenance program so that you only maintain on the evidence of need, which requires, of course, a lot of sensing systems, etc. But this will take away part of the conservatism in the whole maintenance and inspection program of aircraft. So you'll have to be absolutely sure of your models and of your methods to determine the safe lifetime of the aircraft. So that will be a challenge. Another one is non-traditional OEMs. The Sikorsky's, the Boeings, the Bells, helicopters. They have an inherent mindset of developing safe aircraft. They know about fatigue. They've been doing this for years. With the emergence of new unmanned, especially unmanned concepts, there's a whole new generation of OEMs that are not experienced as such. And they will follow the rules, obviously, but they don't have the experience of developing safe helicopters and aircraft. So this is one of the reasons that the US Army is coming up with the RCIP program, Rotorcraft Structural Integrity Program. It mimics the ACIP program that the USAF has been developing for over 40 years now. The main reason is the non-traditional OEMs. Complacency. If you look at the F-15 picture at the bottom, which apparently is losing its cockpit there, it's a trick photo. Of course, it's reconstructed, but it's a real incident which happened about 10 years ago. The investigation has revealed that it was a complacency in the whole aircraft structural integrity program. People have become slack. Structural integrity is not only a technical problem, it's also a managerial problem. And also as high-level management, people have to be aware that structural integrity, you cannot take it for granted. you have to have your procedures right. And this calls for educated people who are aware of that. Aging fleets, and that's very typical for military aircraft. B-52 fleet in the United States nowadays is about, well, the average age is about 54 years or so, and they reckon that by the time they retire, the airframe will have seen 80 years of service. That's a lot of years, and that entails a lot of structural integrity issues. And last but not least, education. The technical studies, at least in the Western world, are not that popular anymore. And if people go to a technical university, they go for the buzzwords, the ICT, the gaming, whatnot, not for fatigue. So there is a risk that we will run out of qualified people in the long run. And in fact, that's already happening. Our Air Force in the Netherlands, and I'm quite sure that more Air Force in the Western world will have the problem, they have a lack of trained engineers. It's very difficult to attract maintenance personnel at all levels. So there is a challenge there. And this may require automation, SH could fill in part of that gap. Anyway, those are my observations from military aviation, but the story continues. I think ICAF is still relevant. We're unique. David already told you. We bring together all aircraft structural integrity stakeholders, and we're very proud of that. Where many conferences are related to fatigue, a very specific audience, we bring together all stakeholders, including both military and civil from all over the world. And as I said, structural integrity, the devil is in the detail, don't take it for granted. So we think that we have a role there to bring that message across. We hope that we can contribute to the education of young engineers. We are constantly thinking of new ways to do that. We have a young researchers session in our conferences. Michel Guillaume, who's there, Swiss delegate, he developed that idea. Yeah, we came up with poster pitches. We have the Jaap Schijve Award for young researchers. Jaap Schijve is my old guru, my fatigue professor. He's still around. He's 92 years old now. He's still active. Not as active as he used to be, but he's there. Anyway, we're here today. We were founded in 1951. We are 67 years of age now. That's the official retirement age in the Netherlands, but we don't think of retiring. We want to go on, especially if you realize that some flying aircraft are older than we are. I think there are a few more years ahead for us. Anyway, I'd like to conclude with a few promotional pitches. 2 upcoming events. Our next conference will be in Krakow in Poland in June 2019. And an important topic there will be additive manufacturing. The conference will be held in Krakow. Poland, well, you know, it's in the center of Europe. It's a very beautiful country, beautiful cities. And Krakow is a very old, ancient city dating back to the 7th century. It's in the National Heritage of the United Nations on the list. As David already said, an important part of ICAF is building networks and collaboration, and we do that through social events as well, as ICAS does too. In 2019 we'll have a very special conference dinner. It will be 100 meters below our surface in the old salt mine of Bieliszka, and I hope there is no Polish native speakers here because I'm not sure about the pronunciation, but it's going to be special. And next in 2021, our conference will be in Xi'an, China, also in June. And Xi'an is the location where the famous terracotta army was excavated about, when was it? Somewhere in the 70s it was discovered. It's a very special place, it's a very nice city. It's home to one of the large aircraft industries in China. And this will be organized by the Chinese Aeronautical establishment. Anyway, what remains now is to thank ICAS for the tremendous honor that you have bestowed upon us for recognizing our contribution to international collaboration, just like ICAS actually. We're somewhat older, but it's a great honor to be recognized by a peer organization in this field. Okay.
I would like to ask all the members, these are the 2018 ICAS award winners, and I will ask our president, Dr. Susan Yang, to come up. You will see the size of this medal. You will want one for yourself. really big. The actual von Karman award. Hope you enjoyed our presentation today. And please continue with the rest of the venue. Please do not go on vacation, okay? We still have a day to go. Thank you. This concludes the presentation.